Let's go, guys. 30 minutes is a lot. We can watch 30 minutes of. Wait, no. We can watch 30 minutes of Andrew Ng, machine learning. Oh my god, machine learning. Andrew Ng, machine learning. Who is your favorite machine learning theorist? I don't even know their names. Borscht. I don't like it when they force me to learn some stuff.
So long as this gamma hat I is greater than 0,
Who cares?
it means that
I like money.
either this is bigger than 0, this is less than 0, depending on the sign of the label.
Oh.
It means that the algorithm gets this one example correct.
Oh my
And much greater than 0, then it means, so if it's greater than 0, it means in the logistic regression case, it means that the prediction is at least a little bit above 0.5, a little bit below 0.5 probability, so at least
honestly,
much greater than 0.
machine learning is amazing for a stretch. Just want to.
So,
Hello. How are you doing? No problem.
is it okay if I?
Yes, sure. Sure.
Oh wait, sorry. You're recording.
Yeah,
I will let you be. No, sorry about that. Sorry.
no problem. Damn, guys, we took over the place.
I'm going to define the function margin.
I don't feel well, right?
To be gamma hat equals min over I of gamma hat I, where here I equals ranges over.
It's not right, dude.
So this is the worst case.
I won't put
definition.
this
So
online.
This definition of a function margin on the left, we
I
define
may
the
put
function
it.
margin with respect to a single training example, which is how well are you doing on that one training example. And we'll define the function margin with respect to the entire training set.
It
as
cannot be
how
all the time like that. People come and just holding the room. It's a common place, so.
well are you doing on the worst example in your training set. This is a little bit of a brittle notion, and for today, we're assuming that the training set is linearly separable. So we're going to assume that the training set, looks like this, and then you can separate it with a straight line. Because we're assuming.
Now that everything is just funny, why are you recording this?
We use this kind of worst case notion and define the function margin to be the function margin of the worst training example.
I don't understand it, honestly.
Now,
Why are we recording
the
this?
definition of the functional margin is actually really easy to cheat and increase the functional margin. And one thing you can do, if you look at this formula, is if you take W and multiply it by 2, and take B and multiply it by 2, then everything here just multiplies by 2.
Far bigger than 0.
Right, but you haven't actually changed anything meaningful. Okay, so one way to cheat on the function margin is just by scaling the parameters by 2.
What if instead of 0 we say 1?
All your parameters by 10, and then you've actually increased the functional margin.
Guys, put it in the comments. My head is still thinking about what happened. We are taking the place. Like, so far nobody came. And I think it is their right to, of course. What do I mean? I think like it's a common place. Everybody can come and sit, and it's actually a quiet study room. So if they ask you, I should just be quiet and stop recording. This time the guy was very nice and let us stay here. But in general, well, we can go. So far nobody came, so there was nothing. and this guy let us. But if somebody comes, it's their right to sit down and ask us to be silent. And we can, well, then that's, I can go to my room and record it or something like that. So everything is good, I guess.
One thing you could do is replace. One thing you could do would be to normalize the length of your parameters. So, for example, hypothetically, you could impose a constraint. The norm of W is equal to 1. Or another way to do that would be to take W and B and replace it with W over norm of B and replace it with. Right, just divide your parameters.
Okay, normalize the
by the Euclidean length
Alright.
of the parameter vector W, and this doesn't change any classification, it's just rescaling the parameters. But it prevents the display of cheating on the functional margin. Okay? And in fact, more generally, you could actually scale
Oh,
W
shoot,
by
dude.
any other value you want.
I can get a stretch.
Right? You could choose to replace this by W over 17, and P over 17, or any other value, and the classification stays the same. So we'll come back and use this problem. So to find the functional margin, let's define the geometric margin. And we'll see in a second how the geometric and functional margin relate to each other. So let's define the geometric margin with respect to a single example, which is so let's see. Let's say you have a classifier. Right. So given parameters W and B, that defines a linear classifier. And the equation Wx plus B equals 0 defines the equation of a straight line. So the axes here are x1 and x2. And in half of this plane, in this half of the plane, you have W transpose x plus B is greater than 0. And in this half, you have W transpose x plus B is less than 0. And in between is the straight line given by this equation, Wx transpose x plus B equals 0. So given parameters W and B, the upper right is where the classifier will predict y equals 1, and the lower left is where we'll predict y is equal to negative 1. Okay? Now, let's say you have one training example here. Okay, so that's the training example, xi, comma yi. And let's say it's a positive example. Okay, and so your classifier is classifying this example correctly, right? Because in the upper right half plane, in this half plane, W transpose x plus B is greater than 0, and so in this upper right region, your classifier is predicting plus 1, right? So this lower half region, you're predicting h of x equals
I should do back.
That's why this straight line where it switches.
I don't want to do shoulders tonight, actually. Fuck.
So, what
Oh my
we're
god.
going to do is define this distance
I'm dying.
to be the geometric margin. This training example is the Euclidean distance is what we define to be the geometric.
Like here in the chest,
So let me just
honestly,
write
there's
down
nothing wrong.
this.
But like when it connects to the shoulder, all the pain is here. Oh fuck! Oh my god.
So the geometric margin.
Oh. Geometric margin, guys.
The classifier of the hyperplane defined by WB with respect to one example, xi, yi. This is going to be gamma I equals W transpose x plus B over the norm of W. And let's see, I'm not proving why this is the case. The
Also
proof is
lower
given in
chest?
rationale notes, but the lecture notes
It's
shows
more like
why
this.
this is the right formula for measuring the
Like
Euclidean
the
distance.
edge of
Just
the
put a
chest.
picture up there.
But here,
I'm not putting this here.
there is
because
some
it's a-
pain still.
so this turns out to be the way you compute the Euclidean distance between that example and the decision boundary. And this is for the positive example, I guess. More generally, going to define the geometric margin to be equal to this, and this definition applies to positive examples and to negative examples. And so the relationship between the geometric margin and the functional margin is that the
Stand
geometric
straight.
margin is equal to the functional margin divided by the norm of W.
Oh, honestly, a back day really
Finally,
is the best thing I can have now.
the geometric margin with respect to the training set is, we're going to use this worst case notion
Mm-hmm.
of look through all your training examples and pick the worst possible training example, and that is your geometric margin on the training set. Oh, and so I hope the notation is clear, right? So gamma hat was the functional margin, and gamma is a geometric margin. Okay. And so what the optimal margin classifier does is choose the parameters W and B to maximize the geometric margin. Okay. So in other words, the optimal margin classifier is basically the baby SVM. You know, it's like a SVM for linearly separable data, at least for today. Right? So the optimal margin classifier would choose that straight line because that straight line maximizes the distance or maximizes the geometric margin to all of these examples. Okay. Now, how you pose this mathematically, there are a few steps of this derivation that I don't want to do, but I'll just describe the beginning step and the last step and leave the in between steps to the lecture notes. But it turns out that one way to pose this problem is to maximize gamma W and B of gamma. So you want to maximize the geometric margin. Subject to that, every training example must have geometric margin greater than or equal to gamma, right? So you want gamma to be as big as possible, subject to that every single training example must have at least that geometric margin. This causes you to maximize the worst case geometric margin. And it turns out this is not, in this form, this isn't a convex optimization problem, so it's difficult to solve this without a gradient descent and show that no local optimum and so on. But it turns out that by a few steps of rewriting, you can reformulate this problem as into an equivalent problem, which is to minimize the norm of W subject to the geometric margin. Right? And so it turns out, so I hope this problem makes sense, right? So this problem is just, solve for W and B to make sure that every example has geometric margin greater than equal to gamma, and you want gamma to be as big as possible. So this is a way to form the optimization problem that says maximize the geometric margin. And what we show in the lecture notes is that through a few steps, you can rewrite this optimization problem into the following equivalent form, which is to try to minimize the norm of W subject to this. And maybe one piece of intuition to take away is, the smaller W is, the bigger, right? The less of a normalization division effect you have, right? But the details are given in the lecture notes. But this turns out to be a convex optimization problem, and if you optimize this, then you will have the optimal margin classifier, and they're very good numerical optimization packages to solve this optimization problem. And if you give this a data set, then, assuming your data is separable, and we'll fix that assumption when we reconvene next week, that you have the optimal
Machine learning. I am learning. Machine learning.
Alright, let's break for today. See you guys next Monday.
Alright, good morning. So today, vector machine.
So, in particular, talk a bit more about the optimization problem that you have to solve this four-vector machine. Then talk about something called the representative theorem. And this will be a key idea as to how to work in potentially very high dimensional, like 100,000 dimensional, or million dimensional, or 100 billion dimensional, or even infinite dimensional feature spaces. And this will teach you how to represent feature vectors and how to represent parameters that may be, 100 billion dimensional, or 100 trillion dimensional, or infinite dimensional. Based on this, we derive kernels, which is the mechanism for work with these incredibly high dimensional feature spaces, and then hopefully, time permitting, wrap up with a few examples of concrete implementations of these ideas. So to recap.
Yes, SVM, reparameters, kernel examples, and optimization problems. These are the elements we can consider for learning
on last Wednesday, we started to talk about the optimal margin classifier, which said that if you have a data set that looks like this, then you want to find the decision boundary with the greatest possible geometric margin, right? So the geometric margin can be calculated by this formula, and this is just the derivations in the lecture notes. It's just measuring the distance to the nearest point. And for now, let's assume the data can be separated by a straight line. And so gamma I this is sort of geometry, I guess, derivation in the lecture notes. This is the formula for computing the distance from the example xi, yi to the decision boundary governed by the parameters w and b. And gamma is the worst case geometric margin, right? You would make, of all of your M training examples, which one has the least or has the worst possible geometric margin? And the support vector, the optimal margin classifier, will try to make this as big as possible. And by the way, what you see later on is that optimal margin classifier is basically this algorithm, and optimal margin classifier plus kernels, meaning basically take this idea and apply it in a 100 billion dimensional feature space. That's the support vector machine. Okay. So I saw one thing I didn't have time to talk about on Wednesday was the derivation of this classification problem. So where does this optimization objective come from? So let me just go over that very briefly. The way I motivated these definitions is that given a training set, you want to find the decision boundary parameterized by W and B that maximizes the geometric margin, right? And so again, as VCAP, your classifier will output G equals W transpose X plus B. And so you want to find parameters W and B. They'll define the decision boundary where your classification switch from positive to negative that maximizes the geometric margin. And so one way to pose this in an optimization problem is, is to try to find the biggest possible value of gamma subject to that. Subject to that, the geometric margin must be greater than or equal to gamma, right? So, so in this optimization problem, the parameters you get to fiddle with are gamma, W, and B. And if you solve this optimization problem, then you're finding the values of W and B that defines a straight line, that defines the decision boundary. So this constraint says that every example, right? So this constraint says every example.
It's so difficult, guys, so difficult. Everybody wants to go somewhere and you have to find people, and once you tell them, they say we will come. They say, oh, I have another plan, and they're right. Like, dude, you're adults. Everybody has his own priorities, and we are lucky. We can do a trip or something, do an activity together. We cannot force other people. I wish I could, like, I wish I could. No, you are going to join us. I think if it was that every week, I should have done Tom Platz with Sam. Like, he would make me do Tom Platz. But or Nikos would make me chill. Let's chill here. Yeah, so everybody wants to, everybody has his own priority. If we are all lucky, we can do like activities together. Sometimes it happens, sometimes it doesn't. Let's go back to machine learning. He didn't say anything to me. Let's be honest.
This is.
He didn't say anything.
And you want to set gamma as big as possible, which means that you're maximizing the worst case geometric margin.
Maximizing the worst case.
So the only way to make gamma, say 17 or 20 or whatever, is that every training example has geometric margin bigger than 17, right? And so this optimization problem is trying to find W and B to drive up gamma as big as possible and have every example have geometric margin even bigger than gamma. So this optimization problem maximizes it causes you to find W and B with as big a geometric margin as possible, as big a worst case geometric margin as possible. Okay. And so, does this make sense actually? Right? Okay. Actually, raise your hand if this makes sense.
It makes sense.
Many of you. Right. Let's see in a slightly different way. So let's say you have a few training examples. The training examples geometric margins are 17, 2, and 5, right? Then the geometric margin in this case is the worst case value 2. And so if you solve an optimization problem where I want every example, where I want the
charging my eyes,
min over I of gamma I to be as big as possible. One way to enforce this is to say that gamma I must be bigger than or equal to gamma for every possible value of I, and then I'm going to lift gamma up as much as possible. Right? Because the only way to lift gamma up subject to this is if every value of gamma I is bigger than that. And so lifting gamma up, maximizing gamma has the effect of maximizing the worst case example's geometric margin, which is how we define this optimization problem. Okay. And then the last one step to turn this problem into this one on the left is this interesting observation that you might remember when we talked about the functional margin, which is the numerator here, that the functional margin, you can scale W and B by any number, and the decision boundary stays the same. Right? And so, if your classifier is Y, so this is G of W transpose X plus B, right? So if, let's see, I want to use 2, 1. If W was the vector 2, 1, let's say that's the classifier, right? Then you can take W and B and multiply it by any number you want. I can multiply this by 10. And this defines the same straight line, right? So in particular, I think, let's see, with this 2, 1x, this actually defines a decision boundary that looks like that. If this is x1 and this is x2, then this is the equation of the straight line where W transpose X plus B equals 0. Right? That's 1 and 2. You can verify for yourself. You plug in this point, then W transpose X plus B equals 0. You plug in this point, W transpose X equals 0. And so that's the decision boundary where the SVM will predict positive everywhere here, and predict negative everywhere to the lower left. And this straight line, stays the same if you multiply these parameters by any constant. Okay. And so, to simplify this, notice that you could choose anything you want for the normal W, right? Just by scaling this by a factor of 10, you can increase it, or scaling by a factor of 1 over 10, you can decrease it. But you have the flexibility to scale the parameters W and B, up or down by any fixed constant without changing the decision boundary. And so the trick to simplify this equation into that one is if you choose to scale the normal W to be equal to 1 over gamma, because if you do that, then this optimization objective becomes maximize 1 over normal W subject to
Dude, come on. So expensive.
right? So if you substitute normal W equals 1 of gamma, and so that cancels out. And so you end up with this optimization problem. Instead of maximizing 1 over normal W, you can minimize 1/2 the normal W squared subject to this. Right? Okay. And so that's a rough. I know I did this relatively quickly. Again, as usual, the full derivation is written in the lecture notes, but hopefully this gives you a flavor of why, if you solve this optimization problem, and you're minimizing over W and B, that you are solving for the parameters W and B that give you the optimal margin classifier. Okay. Now, the optimal margin classifier, we've been deriving this algorithm as if, the features xi, let's see, we've been deriving these algorithms as if the features xi are some reasonable dimensional feature, x equals R2, x equals 100 or something. What we will talk about later is a case where the features xi become, 100 trillion dimensional, right, or infinite dimensional. And what we will assume is that W could be represented as a sum, as a linear combination of the training examples. Okay? So, in order to derive the support vector machine, we're going to make an additional restriction that the parameters W can be expressed as a linear combination of the training examples, right? So, and it turns out that when xi is 100 trillion dimensional, doing this will let us derive algorithms that work even in these 100 trillion or these infinite dimensional feature spaces. Now, describing this just as an assumption, it turns out that there's a theorem called the representative theorem that shows that you can make this assumption without losing any performance. The proof of the representative theorem is quite complicated. I don't want to do this in this class. It's actually written out. The proof of why you can make this assumption is also written on the lecture notes. It's a pretty long and involved proof involving primal dual optimization. I don't want to present the whole proof here, but I'm going to give you a flavor for why this is a reasonable assumption to make. Okay? Oh, and just to make things complicated, later on, we actually do this, right? So yi is always plus minus 1. So we're actually, by convention, we're actually going to assume that wi can be written, right? So
Representation theorem was a theorem in math, I think. It was about
just make some of the math a little bit faster,
every
easier, but this
space is
this can be represented as a linear combination.
dual or equivalent to the space of linear
So,
functions on it.
let me just describe less formally why this is a reasonable assumption, but it's actually not an assumption. The representative theorem proves that this is just true at the optimal value of W. But let me convey a couple ways why this is a reasonable
Okay, guys, enough. Enough with this boring class. Done. I'm done, but I still will watch. It's good. It's good. We know that they're teaching us stuff that is boring, that's not super. Like, if you don't know that, you think, oh, machine learning is this crazy thing that they are teaching. And now we know that up to the session 6 is just, at least on the theoretical level, it is the stuff we already knew. Not a big deal. We should not be scared of it. We know its foundation up to now, which is good. It's not that I don't care about the course. Whenever he starts talking about real shit, we will pay attention. Still good. And we don't know which class starts to be interesting. So we have to watch it. Alright, I hope you enjoyed. And let yourself waste some time. Dude, who said we should be efficient all the time? I'm telling you, I tell you, it's completely fine if you waste some time. Have a good day.